Here's the first of two little lessons we're going to do on trigonometry. Um, as I have been saying in a lot of these, this is, we fly through this material pretty fast. This is just meant to be kind of an overview, give you an idea of the big ideas in the chapter, the main sort of concepts you want to understand. You might come back to this. And if you're looking at the video, you might come back to this later on and rewatch little bits of it once you've actually got into those types of questions. This is going to cover all the main concepts in 5.1 for Math 052. Little bits for B11 in Math 038. You don't really get too deep into the triangles, but a basic understanding of the angles and sides of a triangle is needed. Math 053, this is a funny one as usual. There's no trig in Math 053, but you will run into trigonometry again in your 07 level math courses, depending on which ones they are, and it'll be expected that you know all of the 052 trig, which if you did 052 is great, but many people assess directly into 053. They've never done 052, and the last time they saw trigonometry was in high school or maybe never. So if you have not actually done Math 052, it might be useful just to get a feel for the basic ideas of what's going on in these two lessons. So, angles. An angle is a way that we use to measure a rotation. So if you have two lines, we imagine starting at that red line somewhere along there and rotating as if you're going in a big circle, but then you stop at the blue line, kind of like that. And I had to draw those by hand with my mouse, so my little rotating arrows aren't very good, but there's nothing that did the job in the program I was using. So there's an angle. The place where those two lines meet we call the vertex, and we usually label it with a capital letter, and we also use that capital letter to talk about the angle. We'll often use that little symbol right there, angle A. We often also don't bother because it gets to be really annoying writing that little angle symbol in every step of your equations for every angle that's there. So we generally just understand once we're into these types of questions, we use capital letters for angles and small letters for distances, as you'll see when we get into the triangles especially. So there's a bigger angle. So you can see again we are rotating from the red to the blue, but this one we go all the way around, over halfway around a full circle, right? So a bigger rotation, a larger angle. We use degrees to measure angles, which most people are familiar with because we have a lot of, we talk about angles in a lot of different ways. Maybe not angles like 60 degrees, but lots about angles like 90 degrees and 180 degrees in our sort of everyday life. So we use the degree symbol. And if I were to estimate for you what those angles are, just roughly, that angle A there is about 60 degrees, maybe. Angle B, we would say, is about 225. Now, where did I come up with those numbers? Well, a rotation all the way around the circle we call 360 degrees. Again, language that skateboarders and snowboarders are familiar with, right? Doing a 360 means you're up in the air and you spin all the way around. So there we see the blue line is actually all the way around the circle right beside the red line. If we take half of that, so a straight line, that's 180 degrees. And we also use the skateboarders and snowboarders use that too, but also we use that in a lot of different ways. Like if a politician takes a 180 on a position, that means they've changed their mind entirely, right? They now say the opposite of what they used to say because those two red and blue lines are pointing in opposite directions. If you cut that in half again, you have what we call a right angle or a square corner, and we usually use that little square there to show that it's a right angle. Theoretically, if that's not there, it might look like a right angle, but how do you know it's not 89 degrees or 91 degrees? So theoretically, we try to put that there whenever it's a right angle, although sometimes we forget and just assume. So those are some common, I've already talked about this, but those are some common angles that we use in everyday life. They all just come from the fact that we decided to call a full circle 360 degrees. If you're wondering where that came from, well, I could talk for an hour on that, but I'm not going to. But it all goes back to the Babylonians originally, and then interaction with that with some other cultures. Anyways, we base 60 number systems and cool stuff like that. So a full circle is 360. Half of that is a straight line, 180. Half of that is a right angle, a square corner. Any two angles that add up to 180 are called supplementary angles. You will need to know these words, but of course you do have a handwritten resource sheet you can use, so you could write these down. Two angles that add up to 90 degrees are called complementary angles. So there's an example of supplementary angles, and you see that adding if you start to rotate, I didn't put the rotating in here, but if you rotate 30 and then another 150, you are at a straight line. That's supplementary angles. There's a couple complementary angles. If we start down here and rotate up to that line 20 and then keep going another 70, we have gotten to 90 degrees. So add up to 180 supplementary angles, add up to 90 complementary angles. So if we are asked to find the angle that is complementary to 42, well, that's simply going to be a matter of subtracting from 90. 48. Why don't you try the second one there? 20 seconds. Okay, so if we have two angles that add up to 180, they're supplementary. So if one of them is 163, subtract from 180, and you will get the other one. And you can always double check these, right? What's 48 plus 42? Adds up to 90. What's 17 plus 163 adds up to 180. Supplementary angles. The questions on these, they start to, as math teachers are, it's not enough to just ask you to subtract from 90 or 180, but they start to get into these word problems. So this, you're going to find, is very similar to some stuff we did during the formula solving lessons we did with perimeter and stuff, where they would set up these equations. So here we got two angles and the word problems for Math 053 students in the equation solving unit. Two angles are supplementary. The larger angle is 3 times bigger than the smaller. What are the angles? So how are we going to set this up? Well, let's get a variable in there. Let's let A be the smaller of the two angles. Now, what do we know? We know the larger angle is 3 times bigger than the smaller one. How do we say that in math? The larger angle is 3 times A, 3A. So there's the two angles, A and 3A, the smaller one and the bigger one. Now, what do we know about those two angles? They are supplementary. That means they add up to 180. And now it's just a matter of putting those two angles in. The first angle is A, and the second angle is 3 times bigger, 3A. And those two angles add up to 180. So again, the hard part of these questions is building your equation. Once you have this, we go back to our basic equation solving. Remember, this is 1a here, so 1a plus 3a makes 4a. Divide both sides by 4, because that's how we get the a by itself. On the left, the 4's cancel. On the right, 180 divided by 4 is 45. Now I'm kind of going through the equation solving bit first because we've done this quite a few times now. If you need to slow that down and make sure you remember how to do that, that's fine. Or you could go back and take a look at those formula solving, working with formula videos again. These types of questions, the smaller angle is 45, because we got A is 45, and remember A was the smaller angle. What's the bigger angle? Well, we know it's 3 times bigger, so 3 times A is 135. So our two angles are 45 and 135. They're going to give you a whole bunch of variations on this question. This was one angle is 3 times bigger than the other one. You could have one angle is 40 more than the other one, and they're supplementary. So your angles are A and A plus 40, and you add them up to equal 180 and solve the equation. They're all a matter of setting up that equation and solving. On to triangles. Triangles are 3-sided figures like that one we have drawn right there. As we talked about before, we use capital letters to name the angles. Also, for those would be called the vertices of the triangle. The vertices is plural for vertex. So you would say this corner is called A, this corner is called B, this corner is called C. We also use capital A to represent this rotation, this angle, capital B for this angle, and capital C for this angle. And then we use small letters to label the sides. And the math people came up with a nifty little convention which helps us not have to explain or draw a diagram every time or explain which side is which. So take a look how across from angle A is side little a, across from angle B right here is side little b, and across from angle C is side little c. And so if they just start talking about capital ABC and small abc, or XYZ, or MNP, or whatever letters they choose to use, you know that the capitals are the angles in the triangle and the small letters are the sides across from the same angle with the same letter. So here's something that turns out to be true for all triangles. If you take the three angles and add them up, no matter what the triangle looks like, those three angles will add up to 180 degrees. So just like complementary and supplementary, this gives us some practice questions. So let's say that angle C is 30 and angle B is 70, and we've drawn them into the triangle there. You can see angle C is 30 degrees, angle B is 70 degrees. What is the measure of angle A? You could just subtract from 180. I'm just going to set this up as an equation just so you see, because again, the questions get harder. If it's a nice simple one like this, by all means, just go 180 minus 70 minus 30. But as soon as they start to get a little more tricky, you want to set it up like this. Your three angles are equal to, added together, are equal to 180. Plug in what you know. You know B is 70, as C is 30. Now we know that plus 70 and plus 30 on the left becomes minus 70 and minus 30 on the right from our equation solving. What did we really just do there? We subtracted 70 from both sides and subtracted 30 from both sides, which made this 70 and this 30 go away and become a minus 70 and minus 30 over there. And now just subtract to get 80, like so. Again, probably a little more of a setup than you need to do on this one, but it helps you get the idea for when they twist up those questions a little more on you, which I think we're going to do here. You can always double check this. 80 plus 70 is 150, plus 30 is, yes, 180. So we got the right answer. A right triangle is a triangle where one of the angles is 90 degrees, like that one right there. And remember, we use that little square symbol in the corner to tell us it's 90 without actually writing 90 in there. So we know that one of the angles here is 90. So let's imagine a question here. We have a right triangle. That's a piece of information. One of the angles is 34 degrees. What is the other? Now, if you're thinking, wait, there's three angles in a triangle. What do you mean one of them is 34? What's the other? Well, remember, also one of them is 90 because it's a right triangle, right? So we do have three angles here. A 90-degree angle because of that, a 34-degree angle, and the one we want to find. So there's a picture of the triangle, which you don't necessarily need to draw, depending how good you are at visualizing what's going on. And let's create a variable for that angle we're trying to find. We'll call it x. So again, the angles in a triangle must add up to 180. So what are the three angles? The one we don't know, x, plus the 90 because it's a right triangle, plus the 34 that they told us, those must all add up to 180. Those things that are being added on the left become subtracted on the right. And there we go, 56 degrees is the third angle. And you can double check that. 56 plus 90 plus 34, double check, and those do indeed add up to 180. Okay, similar triangles. So again, there's a lot of big ideas here we're overviewing just really quickly, right? You got to get in there and practice the variety of questions that come up on each idea: complementary angles, supplementary angles, triangles, right triangles. Now we're on to similar triangles. Similar triangles are when two triangles have exactly the same angles, and just one is bigger than the other. If they're the same size, they're the same triangle, right? So they wouldn't be similar, they'd be the same. So similar is the word we use when two triangles have the exact same angles. And you can see it's just like one is a blow up of the other, right? Or a miniaturization of the other if you want. So here, both of these triangles have angles of 50 in red, 20 in blue, and 110 in orange there. So all three angles match, even though this triangle is definitely bigger than that triangle looking at the measurements. The notation we use for this, as we say triangle ABC, is similar to triangle DEF, and we use this little symbol there. So you see we use the triangle sign, triangle ABC, similar to triangle DEF. Do you notice I kept the letters in the right order too, starting at the 50 degrees to the 110 to the 20? It doesn't matter which order you put the first one in, as long as you then put the other one in the same order, right? The matching order. Okay, so who cares if two triangles have all the same angles? Well, it turns out that if two triangles are similar, then here we get ratios again all over the place in Math 052. The ratios of their corresponding sides are equal. So here we have been told that triangle ABC is similar to the statement right here, meaning all the angles match, similar to triangle XYZ. And we've been given some of the measurements in each one, but in each triangle we don't know one of the sides. We don't know what A is. We don't know what Y is. And notice we don't even know what any of the angles are. So we would be kind of stuck if we didn't know that they were similar. So we're going to do one of these. We're going to find A, then I'm going to get you guys to try Y. Here's what you want to do on these questions. Start the ratio with a corresponding pair you know both of. So corresponding pairs, like this side here is 3.2, and its corresponding pair down here is Y. We don't know Y. Okay, we don't know both of those. This one down here is 4.5. Its corresponding side up here is A, which we don't know. But look along the top. Side AB, this one here we know is 4. Its corresponding side is 3. There we go. There is a pair of corresponding sides that we know both of. That's how you start your ratio, with that one. Then grab a pair with one of the things you want to find. Well, we want to find both A and Y. Let's find A first. So I'm going to grab A, and its corresponding side down here is 4.5. And that is the second half of my ratio. That is the hard part of the question, because the rest, if you've done chapter 3, I could have just popped that on there for you, and you would know where to go from there, right? Turn those into fractions. Find the cross product that doesn't have a variable in it. You're going to multiply those two and divide by the other one. And that's just a little shortcut that we know works in this special situation, right? So A is the green 4 times 4.5 divided by the orange 3. And if you punch that into your calculator, you will get an answer of 6 for A. And it never hurts on these questions to look at the question and make sure 6 makes sense. You know, if this is 4 and that's 3.2, does that look like about 6? Now, sometimes they won't be drawn perfectly to scale, but if you get an answer of 820 on this triangle, you probably made a mistake. Or if you get an answer of 0.3, I would sometimes have that in classes. Students would, like a word problem, their final answer, the building is 0.2 meters tall. And I think you should have probably caught that that answer didn't really make sense and gone back to try and find your mistake. So you try solving for y using the same process. So start with the pair you know, then the pair that with the thing you want to find, and use ratios to solve. Okay, let's give this a try. So we always want to start with the pair we know. We technically now know this pair, right? A is 6, so 6 and 4.5. I would avoid using that one unless you have to, because what if you made a mistake when you solved for A? So you might as well use the pair that you definitely know for sure, which is the 4 and the 3. Now the A and the 4.5, sorry, the 3.2 and the Y are a corresponding pair in this case. Turn them into fractions. Identify the cross product without a variable, divide by the other one, and you will get 2.4 on this one. All right, so that is the basic idea of working with similar triangles. It's all ratios. Oh, by the way, I will mention the book describes this a little differently. They jump kind of straight to the fractions, and they will give all three fractions being equal. I find that throws students off because they're like, well, what do I do when I have two equal signs in my equation? You don't. You have to pick the pair that you want, which is what we're doing here, right? We're picking the pair we know and the pair we want to find. The pair we know and the pair we want to find. I find that this explanation of how to approach these questions clicks better for most students. If you like what the book does, no problem, of course. But if it kind of confuses you, and this is making sense, then by all means, just set up the ratios, and this works great for you every time. A real quick little side bar here, which is going to help us in our next trig lesson. Right angles, we use them all the time, and it turns out that it's very handy to name the three sides in a right triangle. This side over here, the side across from the right angle, you might recognize is always going to be the longest side in any right triangle. These two here have to be shorter than this long one over here. We call that the hypotenuse. So the one across from the right angle, it's probably a word you've heard before, but maybe not. We call the hypotenuse. It's a Greek word. Greek word for the side across from the right angle. No, I don't know what it means in Greek, if it means anything other than that. The other two we call the opposite and the adjacent, but here's a little bit tricky. It all depends on which angle you decide you're working from. There's going to be some equations we set up, and you have to know which angle you're working with before you can decide which is the opposite and the adjacent. We call the angle we're going to work with the reference angle. So if we decide that angle down there is our reference angle, then the one across from it is the opposite. Notice that can't possibly be the hypotenuse, right? Because you're not going to work from the right angle. The right angle is the right angle. You're going to work from one of the other two. And then kind of the leftover one is the adjacent. It's the one that the reference angle touches. That's why it says adjacent, other than the hypotenuse, which already has a name. But if we switch to the other angle up there, if that's the angle we decide it's going to be most useful to work from for whatever question you're looking at, then notice the opposite and adjacent switch places with each other. The opposite is the one across from the reference angle. The adjacent is that third leftover one. So they're opposite and adjacent in those positions. If this is our reference angle, right? Opposite across. Opposite and adjacent in those positions if this is our reference angle. The hypotenuse never moves. The hypotenuse is the hypotenuse. It's across from the right angle. And as we mentioned, you don't choose the 90-degree angle as the reference angle. That just wouldn't work. The reason everything works when we get into these next lesson is because there is a right angle over there somewhere, and then we work with the other angles. Okay, last thing for this quick 5.1052 overview. Pythagoras, famous Greek mathematician, lived about 500 BC. And He was not the first person in history to discover Pythagorean theorem. It might surprise you to know it was known way before him by many cultures and as well by the Greeks before him. But he managed to be the one who gets all the credit because he made it famous. So, what is Pythagorean theorem? Well, it says that in a right triangle, there's a special relationship between the sides. C squared equals A squared plus B squared, where C has to be the hypotenuse. C has to be the longest side. This will be true for any right triangle you draw. So if you pick up a ruler and draw two straight lines, being very careful that they intersect at very close to a right angle, and you measure the three sides and plug them in, you will find that you square A and you square B and then you add them together. It's the same as taking C and squaring it. This comes up everywhere. I can't even begin to talk about all from calculus to the trades to pretty well any statistics. Pretty well, even though it seems like it's just about a triangle, it ends up having implications for all kinds of different fields. So here's an example. We've been asked to calculate C, and I didn't have to call it C. I could have called it X. I could have even really messed you up and called it A or B if I had wanted to, and that might happen sometimes. I called it C this time. So we can see, though, the key is that C is the hypotenuse. That means that there's our Pythagorean relationship. C squared will be equal to 10 squared plus 21 squared, the other two sides. If you are wondering, how do I know which one is A and which one is B? The answer is it doesn't matter. Think about it. 10 squared plus 21 squared will be the same as 21 squared plus 10 squared. All that matters is that those ones on the right are not the hypotenuse, and this one on the left is the hypotenuse. All right, we can work out these numbers now. 10 squared is 100. 10 times 10, or using your squared button on your calculator. 21 times 21, or again, get used to using your square button, 21 squared. You'll get 441. We can add those together on the right, getting 541. And now, here's why I said that Math 052 students, even though they've never actually learned roots, actually need to use them as part of, comes up in both Chapter 4 and Chapter 5 in different ways. So here we know that the hypotenuse side C squared is 541. We don't want to know what C squared is, though. We want to know what C is. Well, now is when you pick up your calculator and use the square root button to approximate the root of 541, and you will get to two decimal places. Question set up here to the nearest hundredth, right? To two decimal places, 23.26 centimeters. So that's the basics of Pythagoras. Now, in this question, I gave you the two, the A and the B. They're called the legs over here. This is the hypotenuse. These are the two legs, and it doesn't matter which one's which, as we said, because you're just adding them. We could have turned that around like this one. And notice I have the hypotenuse is this one down here. We know the hypotenuse. We know one of the legs. We are missing the other leg. So let's set this one up. Again, we're going to use Pythagoras. But now when we plug in the numbers, that 15 on the hypotenuse goes in for C. And then the other two, order doesn't matter, x squared and 11 squared, right? So again, the hypotenuse is the one by itself. The other two, in either order, doesn't matter which, are the A and the B. Okay, I want to get that x by itself, so I'm going to take that plus 11 squared there on the right, and I'm going to subtract it over to the left. You might have also turned those into squared those numbers first, which would also be fine. Sometimes they get really big, which means a whole bunch of extra writing if you do it that way. That's the only reason I would tend to do this. I would subtract that 11 over first. Or when you get good at it, you realize that when you're finding the hypotenuse, I'm going to go back for a sec. When you're finding the hypotenuse, you add the squares of the other two, and look what happens when we're finding one of the other sides. We subtract the squares of the other two, is what ends up happening once we solve that equation. Turn everything into, calculate what those numbers are, 15 squared and 11 squared. Using your calculator, subtract. We get x squared is 104, but of course we don't want x squared. We want x, so we need to go do the opposite of squaring, which we saw in our last little lesson on powers and roots, is square rooting on your calculator. And this question said to the nearest tenth, so I put my answer to 1 decimal place, 10.2 feet. And that's the basics of Pythagoras. I would say the two biggest ideas in this lesson are the similar triangles and Pythagoras. That's going to take up the bulk of your questions. There is also the stuff on supplementary and complementary angles and angles in a triangle adding up to 180 and the word problems that come up around that. But the big ideas are Pythagoras and similar triangles.